semantics, the substitution model is usually used. So the substitution model has been widely adopted for formalizing programming languages. However, it's not without drawbacks. So for example, reasoning about binding and substitutions is tricky. So in general, you need to define variable names, questions, and alpha equivalents. And in particular, reasoning about the Bruno indices will be very tedious because you will need to prove a lot of properties about the interaction between shifting and substitutions. And there are also gaps between the substitution model and the actual implementations. So every time we have a function application, we need to reverse the term, which will be very costly. And the size of the term will increase dramatically after the substitution. So in practice, substitutions are usually delayed and explicitly recorded. Besides substitution model, we can also have environment-based semantics. So for example, we can have natural semantics or business semantics, which can be formalized using environments. So in this way, function closures appear naturally, but they can only appear at one time. So programmers are not allowed to write any function closure in their programs. We can also have explicit substitutions, which enable a general form of closures. So here, the expression E here is not restricted to a function. It can be any real form expression. And programmers are now allowed to write closures in their programs. And we can also have closure tabuli, which can be regarded as a library form of explicit substitutions because they use weak reduction. So there is no shifting of the Bruno indices, and the Bruno indices fit very well with the closure tabuli. And it's very easy to derive oxygen machines for the lambda calculus with the closure tabuli. If we go one step further, we can have first class environments, which can be passed as arguments, can be returned as results, and can be stored in variables. So in tabuli with first class environments, we can have a very general form of expressions, which we call boxes in our work. So basically, in a box, we evaluate E2 given an expression E1. So E1 here is an expression. It's not a capital E. It could be any real form or real type expression. But the existing word for the first class environments has a very complicated story for binding, and the proofs of meta theory are typically complex. So in this way, we advocate for an alternative way in formalizing programming languages by using our own small stack environment-based methods. So basically, we want to simplify the notorious binding problem in formalizations. We use the Bruno indices, but we don't define or reason about shifting or substitution. Our semantics is closer to implementations because we use closures and environments directly. And our semantics naturally enables constructs for first-class environments without significant additional complexity. All of our proofs of meta theory are quite simple. And our semantics comes with additional expressive power. Basically, we can have controlled environments, a notion of sandboxing, and a simple form of first-class modules. Basically, we can have programmer-controlled environments if we have first-class environments. So basically, there are three operators on first-class environments. The first one is the query operator, which unifies the covered environment. And the second one is the box, which reflects an expression into an environment. And we can also have the merge operator, with which we can compose two environments. So now programmers are allowed to manipulate environments very directly. So here is an example. In the second line, we first use the query construct to unify x equals 1 for the first line. And then we use the merge operator to compose x equals 1 with y equals 2. And then we can evaluate y plus x in boss using the local environment. But note that the expression to be evaluated in the boss can only assess local environment. So the expression in the boss cannot refer to the global environment. So in this example, in the boss, we don't have any information about x in the local environment. So this program does not time check because x refers to nothing. Basically, our notion of process provides a form of sandboxing because computations in process can be run in an isolated and controlled environment. So our notion of first-class environments can also enable a simple form of first-class modules. So here are some simple modules. Basically, the first module contains some utilities of I/O, and the second module requires a print utility, and use that print utility for the sort and print-based functions. We say that the second module is not fully implemented because we can implement the second module with the print function for the first module, but we can also have different implementations with other print utility for other modules. Okay. So we can also define a main module in a similar way. So basically, in these examples of simple modules, capabilities are supplied as arguments. So we can determine the authority of a module by simply examining the arguments. Okay, so basically these simple modules can be encoded in our characters. So if a module is not fully implemented, then we can use a lambda abstraction to model that module. But note that these lambda abstractions are forced with the empty environment. So this means that functions inside a module can only rely on imports. So the functions inside module cannot refer to any global variables or any global environments. So now we can fetch the I/O utils, and the main module from the global environment, and then we can construct or create a local environment. And then we can also pass capabilities for the local environment to the main module, and we evaluate this implemented main module in the box. So basically, now we can manipulate environments with a very high level of flexibility. Okay, so we concretize our ideas into calculus with first-class environments. So our types are basically simple types, but in our setting, types and typing contexts are unified. So a list of typing assumptions, gamma, is simply encoded as an exception type. And this is our definition of expressions and values. So in particular, we have the merge operator, we have the query, and we have process. And similarly to the unification of types and typing contexts, we also unify one-time environments and values. So now an environment is encoded as a merge of values. And our recursion relation is a ternary relation. We use the value B here for checking the current one-time environment. Okay, so this is the typing rule and recursion rule for the query operator. Because we unify types and typing contexts, and we unify one-time environments and values. So these two rules are quite simple. You can just fetch the current context and fetch the current environment. With the query operator, we can have tuple indices and labels as static sugar because we have congestion and label symmetry. In our work, tuple indices and labels have two different roles. So basically, look up by the tuple indices ensures alpha equivalence. This is very important because we want to prove the operational correspondence to some more standard models, such as the standard lambda calculus, which enjoys alpha equivalence. And the local bilaterals ensures that we can have parallel modeling of declarations and modules. So we think that keeping both of the parentheses and labels leads to a clear formalization, and at the same time, we don't lose any expressiveness. Okay, and this is the target rule for bosses. So basically, we use the type of E1, which is number 1 here, to check E2. So, so E1 here contains all the information for E2. So E2 can only refer to gamma 1. It cannot refer to global context gamma. Okay, and our evaluation of bosses is from left to right. So in the boss, the E1 will always evaluate to a value E1 first, and then we use that E1 to evaluate E2. And after E2 becomes a value E2, we just fetch that E2 for the boss as the final result. And our semantics is small step. So we also use bosses in the meta reduction because we want to store the intermediate result in the box. Okay, so we prove the type soundness in our calculus. So basically, our notion of semantic type soundness is generalized because one-time environments are involved in our progress and preservation theories. So basically, there is an extra condition saying that that is a value E is real time. And if the expression E is also real time under that environment, then this expression E is safe. And the proofs of these two theorems are very simple because we don't need to reason about substitutions. And the standard theorem can be obtained by making the environment as an empty environment. Okay, so we also consider semantic type soundness. So our value interpretation of types is quite standard, but we don't need to include any substitutions in our definitions. So in particular, in the case of the arrow types, we don't need to include a meta-level substitution. We can just use our notion of box in the multi-step reduction. And our notion of semantic typing is also standard, but first-class environments enable the counting of concepts. So now, to prove the soundness of semantic typing, we don't need to define a simultaneous substitution. We can just use our value E here because we basically unify values and environments. And we don't need to define an extra context relation. We can just use our value interpretation of types because the types and typing contexts are totally different. And we don't need to include a meta-level substitution in the multi-step reduction. We can just use our environment semantics, which contains one-time environment. Okay, so there are more stuff in the paper. So besides small step semantics, we also define an equivalent big step semantics. We also prove the operational correspondence to other models, such as simply type lambda calculus and closure calculus, to show that our semantics is closer to implementations. We also compile our semantics to an abstract machine. And we also extend our calculus with beautiful references. And all of the technical results are formalized in the conclusion. Okay, I think that's everything I wanted to talk about our work on first-class environments. Thank you.
Thanks, Jinhao. Do we have questions? Jinhao? Yes, please. We will try it first, then we can give it to the next speaker.
Hello?
Excellent.
Okay, great. This was an excellent talk. I really enjoyed watching it. because like substitution feels like one of those things where when you first look at it, it's like, I don't know, this simple little thing. You just substitute the variable. You just substitute the variables. But then, yeah, you run into all these like tricky cases in different programming languages, and it ends up just being this messy thing to implement.
That was all me. Apparently this works.
So yeah, I appreciate it.
Okay.
Hello. So yeah, I appreciate getting to look at this system, and it was a very thorough and good explanation. So I appreciate you taking the time to share this with us. I just wanted to look back at the beta reduction rule because I didn't have a lot of time to look at it in your earlier slide, and maybe you could just, I guess, elaborate if there's anything particularly special about it. Maybe that distinct from the standard beta reduction rule. Oh, is it? Hello. Can you hear me now? Okay. I just wanted to take a look at the beta reduction rule again. If you could pull that slide up, because I just didn't get to really see it, and maybe you can elaborate on some of the distinctions from the standard beta reduction rule in the STLC. Okay. Does this? Huh?
Right. So in our beta reduction, we use a box instead. Okay. So does this answer your question?
Yeah. Let's take this offline.
Sure.
Excellent work. So in your slide, you mentioned some previous work also on the first class environment. Can you elaborate a few connections or what's your improvement comparing to previous work?
Yes. So in previous work on first class environments, they use the names for variables, and to define the fresh variables and alpha equivalence, the work needs a lot of mechanism. So the proofs are very complex. So it's not sure whether their proofs can adapt in a theorem prover.
Okay, thank you.